these are the examples from Chapter 11, Math 102, sections 1 through 4. It's the probability chapter. And the first section is 11.1, the fundamental counting principle. And with your fundamental counting principle, what you're going to do is you're going to look at each of the different possible outcomes and how many times that outcome occurs. And you'll multiply those outcomes together to get the total number of outcomes available or possible. So for instance, for the first one, you have 3 different items. You have pants, shirts, and shoes. So to figure out how many different outfits you're going to make, using your fundamental counting principle, you are going to take the number of pants you have. You have 2 different pairs of pants, times the number of shirts. You have 5 shirts, and then times the number of shoes to get your total number of outfits. So you look at each of the 3 different items, the pants, the shirts, and the shoes, and then you multiply them together. So 2 times 5 is 10. 10 times 3 will give me 30 different outfits. For the next one, a restaurant offers sundaes you choose from 4 different flavors of ice cream, 2 different sauces, and 10 different toppings. So again, here we have 3 different things. We have ice cream, we have sauces, and we have toppings. There are 4 flavors of ice cream, 2 different sauces, and 10 different toppings. So when we multiply those together, 4 times 2 is 8. 8 times 10 will give us 80 different sundaes that we could make. So here we're continuing with our fundamental counting principle. And our next question is you're going to take a multiple choice test with 5 questions. So that's our 5 different options. So when I draw it, I'm going to put 5 options. So 1, 2, 3, 4, and 5. And each question has 4 answer choices. So it's multiple choice. All 5 questions are multiple choice. There are 4 answer choices each. How many different ways can you answer the test? So for my first question, it's multiple choice. I have 4 answers to choose from. And we're going to assume you don't have any idea what you're doing, so you're just guessing, so we can see how many different ways you can answer it. For the next question, it is also multiple choice, and there are 4 different choices. So that's going to be another 4. The same thing for the third, 4th, and 5th question, because they all have 4 choices. So this is the same as doing 4 to the 5th power, or when you multiply it out, you have 1,024 different ways to answer that test. Okay, our next question, you're going to take a test with 4 true-false questions and 3 multiple choice questions. So now I have 7 questions. I have 1, 2, 3, 4, 5, 6, 7. The first 4 are true-false, and if you know true-false, there's 2 choices there. So for my first 4 spaces, I'm going to put 2 because each question I can answer true or false. So I have 2 choices for the first 4. Now the next 3 are multiple choice, and the multiple choice questions each have 3 answer choices. So for the next 3, I'm going to have a 3 for each one because each multiple choice question has 3 choices. So again, this is the same as doing 2 to the 4th power times 3 to the 3rd. Or when I multiply it out, there are 432 different ways that I can answer that test. So different, think of it like answer keys that you could have. Let's see, our third question here says license plates in a particular state display 2 letters followed by 3 numbers. How many different license plates can be manufactured in this state? So we have, first we have 2 letters, and then we have 3 numbers. Let me put my numbers. So my 2 letters, for that, it doesn't say we can't use any certain letters in the alphabet. There are 26 total letters. It does also not say that we can't repeat. So for each of the letters, I have 2 options. I have 26 options total. then my numbers is going to be a single digit. And here's where it can be a little tough. If you think about our digits, though, we can use the digits 0 through 9. So even though we think there's 9 digits there, there's actually 10 because we count 0. And again, it doesn't say we can't use repeats. So repetition is allowed. So when we multiply this together, we will end up with 676,000 different license plates that we can make. All right, and our last one on this slide is how many different 4-letter radio station call letters can be formed if the first letter must be a W or a K. So we have 4 letters that we're looking at. That's going to be our total number of spaces we're going to have. And the first letter must be a W or a K. So we only have 2 options for the first letter. But then for the next 3, it doesn't give us any specification. So we can use any letter of the alphabet. So we have 26 choices there for the second letter, 26 for the third, and 26 for the fourth. And when we multiply that together, we end up with 35,152 different call letters that can be formed. Okay, so next we have Norma is creating a new game that has 15 different cards. And how many ways can you deal out the 5 cards from Norma's deck? So we're going to say she's going to deal out 1, and you're going to keep it. And she's going to deal out another to you, and you'll keep it. So for this one, for the first card, we have 15 different cards. I have 15 options. But if I keep the first card, then the second card, I only have 14 options. Then I will have 13, 12, and 11. And when we multiply that all together, we get 360,360. All right, how many different orders can you arrange all the letters in the word smile? Well, smile has 5 letters. So I'm going to make 5 spaces. And here, it is going to be very specific. Like I have 5 letters to choose from. So for the first letter, I can choose from all 5. But if I use one of the letters, for the second letter, I could only have 4. The third will be 3. The fourth will be 2. And the last one will be 1. So if I multiply that together, I get 120 different ways to organize the letters in Smile. Next, we are looking at how many ways can a casting director choose a female lead and a male lead from 5 female actors and 6 male actors. So we're looking for a female lead and a male. So we will need a female and a male lead. Females, we have 5 actors, and males, we have 6. So when we multiply those together, there's 30 different ways I could choose a male and a female lead. And our last one here, for a temporary job between semesters, you're painting parking spaces in a new shopping mall with a letter of the alphabet and a single digit from 1 to 9. The first space is A1, the last space is Z9. How many parking spaces can you paint with distinct labels? So we have a letter and we have a number. Letters, they don't specify any special conditions. So we have 26 to choose from there. But the digits are only going to be from 1 to 9. So instead of 10 here, we're going to put 9. And when we multiply it, we'll get 234 distinct options. So this is the start of 11.2, and we're working on permutations here. And here, a permutation is an ordered arrangement of the items, such that no item is used more than once. The problem we just did with smile on the last slide is actually going to be a permutation because we don't use the letters more than once. And we're going to start off here. We need to arrange 5 pictures on a wall. How many different ways can you arrange the pictures on the wall, assuming the order makes a difference to you? So we're going to start it just like we did with our fundamental counting principle. We have 5 pictures, so we have 5 spots. In the first picture, I have 5 to choose from. But once you hang a picture, you can't hang it in two places at once. So we have 5 for the first, then 4, then 3, then 2, then 1. So it gives us 120 ways. Or if you do a multiplication problem where you start at a number and then you count all the way backwards until 1, this is called a factorial. So 5 times 4 times 3 times 2 times 1 is the same as writing 5 with an exclamation point, and that exclamation point means factorial, and it simply means that you start at the number listed and multiply every single number from there and down to 1. Also, 0 factorial always equals a 1. So here we're going to start and practice some factorials. There is a factorial button on your calculator. If you're using a Texas Instrument calculator, if you go to the math button and then arrow over to PRO or PROB, there will be an option for a factorial, which will be, it'll show you the exclamation point. But here they want us to do these problems without using the factorial key. So 8 factorial, we know, is going to be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And that is going to give us, when we multiply it, and you can use the calculator to do 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, but we get 40,320. And I would encourage you to, now that you know how to do it without the factorial button, try the factorial button on your calculator. See if you can find it. It's a little bit different for each calculator. Okay, so for the next one, we have 12 factorial divided by 9 factorial. And I'm going to work on this one down here. 12 factorial, we know, is 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And it's divided by 9 factorial, which is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, we could multiply all of that out on our calculator and then simplify it, but there is an easier way to simplify this. We have all factors here, and I know that when I have a fraction, if I have 9 over 9, and it's a factor there, that equals a 1. So I can cancel the 9s out, and that gives me a 1, as do the 8s, the 7s, the 6s, the 5s, 4, 3, 2, and all the way down to 1. So that all equals a 1. So it's like having this big times a 1 there. We got rid of the bottom. We don't have the bottom anymore. So really what we're doing here is we're doing 12 times 11 times 10. And when we multiply that out, it gives us 1,320. So it makes it a little bit easier. For the next one, we have 7 factorial divided by, and here you want to do those parentheses first. 5 minus 2 factorial will give us 3 factorial. So again, if we write it out, we have 7 times 6 times 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1. But my 3, my 2, and my 1 will cancel. So we're just going to multiply 7 times 6 times 5 times 4. And when we multiply that, we get 840. For the next one, this one is a big one, and your calculator won't necessarily be able to put it all in. It won't do 102 factorial. It's too large, and it won't do 99 factorial. I think it stops at 69 factorial. But we know that from 99 down, those values are going to equal a 1 and cancel. So we're really going to have 102 times 101 times 100 for this problem, because from 99 down, they will equal a 1, and so it'll be like 102 times 101 times 100 times 1. And that gives us 1,030,200. And then our last one is 9 divided by 3 factorial, and because it's in the parentheses, we'll do the 9 divided by 3 first, which will give me 3 factorial. And we'll do 3 times 2 times 1, and that gives us a 6. Okay, we're still looking at permutations, and when you have permutations, there is a formula that we can follow. If you have a permutation and they give you something like 9p4, that means that the n is the total number of items you have, and r, or the number on the right, is how many items you're choosing. So if I have 9 pictures and I'm choosing 4, I need to find out how many different ways I can arrange those 4 items. Now, with a permutation, because the order matters, it's going to be very similar to a factorial. So you will see we have 9p4, and if I plug that into my formula, I'm going to have, let me write it over here, 9p4. If I put it into my formula, it would be n factorial. So we'd have 9 factorial over, and then in parentheses, 9 minus 4 factorial, which gives me 9 factorial divided by 5 factorial, which for a permutation will equal 9, if we write it out, it'll be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1. And again, if you notice, what happens is those lower values will cancel out. They'll equal 1. So if we have 9 pictures but we're choosing 4, we would end up doing 9 times 8 times 7 times 6. And when we multiply that, it will give us 30,024. Now, there is a button on your calculator where you can just put this in directly to get your answer. Again, if you go to the math button on the Texas Instruments graphing calculator and arrow over to PROB or PRB, there will be an option where it'll have the P for permutation, and what you want to do is type in the 9 first, then go to math, arrow over to probability, find the permutation button, hit it, that'll give you the P, and then type in your 4. And when you do that, you can double check your answer, but you should get 3,024. And if you guys need to, let me know, and I can post a video of how to do that. Our next question says, a club with 10 members is to choose 3 officers, president, vice president, and secretary treasurer. So here order matters because the first person chosen is president, the second person is vice president, and the third person is secretary treasurer. And each office is held by one person. No person can hold more than one office. How many ways can the offices be filled? So here, if we're looking at it and writing it in permutation form, we have 10 total people, but we're choosing 3. So when I do this, it's really going to end up being 10 factorial divided by 10 minus 3 factorial, which will give us 10 factorial divided by 7 factorial. So we're going to end up doing 10 times 9 times 8, and it's going to give us 720 different ways we could choose the 3 positions. Okay, so we're continuing with our permutations here. And we have a radio show where the songs order matters. They don't want to play the same songs in the same order all the time. So they have 13 records to select from and 7 records they're going to play. So they want to know how many different ways they can arrange the segment of the show. So it is a permutation. We have 13 total items and they're choosing 7. So again, it will be equal to 13 factorial divided by 13 minus 7 factorial, which will give us 13 factorial over 6 factorial. And when I do the math, it ends up being 8,648,640 different ways we can arrange all of those records. Now the next thing we're going to talk about is permutation of duplicate items. So if you have items that repeat, in a permutation, you don't want to repeat your items. So if you have duplication, it does affect how many ways you can arrange those items. To show you the difference, let's look at the letters in set and how many ways I can arrange those letters. So I could do set, or I could change it and make it S-T-E, or I could do E-S-T, or E-T-S, and then I could do T-S-E, or T-E-S. So there's 6 different ways I can arrange those 3 letters. But with Anna, because we have 2 letters that are the same, if I can't have repetition, I can arrange it A-N-A, or I could do A-A-N, or I could do N-A-A. But I can't go any further because then I would have repetition. So there's only 3 ways to arrange those letters. There is a formula that you can use if you have repetition. And you're going to start off with the total number of items you have, no matter if there's repetition or not. And then you're going to divide it by your repetitions on the bottom. So if we look at the letters in Dallas, there are 6 total letters in Dallas. So that's my n factorial. And then on the bottom, we're going to divide it by our repetitions. So we have 2 A's and 2 L's, and those are our repetitions in Dallas. So on the bottom, I'm going to divide it by 2 factorial for the 2 A's, and then also 2 factorial for the 2 L's. So if I were to write it out, it would be 6 times 5 times 4 times 3 times 2 times 1 divided by 2 times 1 times 2 times 1. And we'll cancel out what we can, so we can get rid of one of the pairs of 2 and 1. And then when we multiply the top and divide it by 2 times 1, I'm going to end up with 180 different ways I can arrange those letters. If you look at Tennessee, there are 9 total letters in Tennessee, so we'll start with 9 factorial. And then when we do our repetitions, there are 4 E's, 2 N's, and 2 S's. So it will be 4 factorial, 2 factorial, and 2 factorial. And then we'll do 9 times 8 times 7 times 6 times 5 times 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1 times 2 times 1 times 2 times 1. And we'll get rid of the biggest one we can, so the 4, 3, 2, and 1. And then when we multiply it all out, we end up with 3,780 ways. Okay, so now in 11.3, we're looking at combinations. Combinations are a little bit different than permutations. In a combination, the items are all selected from the same group. So we'll be looking at like the number of books we're selecting, picking children to take in like a van for a zoo trip. Each item is used no more than once, and the order makes no difference. So it doesn't matter the order I pick the books in, the order I pick the children in, I just need to pick them. So the difference between a permutation and a combination. A permutation, order matters, but a combination, the order does not matter. So here, we're going to decide whether the problem is a combination or a permutation. The first one says, how many ways can you select 6 free DVDs from a list of 200 DVDs? It doesn't matter the order that I'm selecting them in. I'm just selecting 6 DVDs. So this is going to be a combination. But here, the next one, in a race in which there are 50 runners and no ties, how many ways can the first 3 finishers come in? For that one, when you run a race, you have first, second, and third. So the order does matter. The first person in is the winner, not the third place person. So this one will be a permutation. Order does matter. All right, so our combination formula is a little bit different than our permutation formula. You're still going to have n factorial on the top, and it's going to be divided by n minus r factorial, but then you're also going to times it by r factorial. So for this formula, you do want to know it. Permutations, you can get away without really knowing the formula. if you know how it works. But here, you do kind of have to know that formula. So if I have 30C3, that means that I'm going to do 30 factorial divided by 30 minus 3 factorial, but then also times, on the bottom, 3 factorial. So when we do 30 minus 3, we end up with 27 factorial. So on the top, everything's going to cancel out from 27 down to the bottom. So I'm going to end up with 30 times 29 times 28, and I just canceled out my 27 factorial on the bottom. And then I'll still be left with divided by my 3 factorial. So when we multiply this all out, we are going to end up with 4,060. And there is a combination button on your calculator. I encourage you to try that one out as well. It's it's right below the permutation. I think it's below it. It's either below or above it, but they're right next to each other. And with the factorial button as well. So next, we have a 4-person committee is to be elected from an organization's membership of 11 people. How many different committees are possible? Now this one is a combination because they don't say the committee is going to have certain jobs. They're just selecting 4 people for this committee. So we'll do 11C4, which means we'll have 11 factorial over 11 minus 4 factorial times 4 factorial. So 11 minus 4 is going to be 7. So from 7 down, we'll cancel out. So we'll end up with 11 times 10 times 9 times 8 divided by 4 factorial. And when we do the math there, we end up with 330 ways we can pick the 4 people. Okay, next, we volunteer to help drive children to a charity museum. You can fit 8 in your van. There are 17 total children. So my N is 17, and we're choosing 8. And when you do the formula, fill it in, you end up with 24,310 different ways you can arrange the children or select the 8 children. And then our last one, you have 12 possible books, and you're going to take 4 with you on vacation. How many different collections of 4 books can you take? So we have 12 total books, and we're choosing 4. So when we do the formula, we end up with 495 different ways we can select 4 books. Okay, so here we are in section 11.4 now, which is the probability, looking at probability of events. The first thing we're going to look at is the probability of rolling dice. When you roll 2 standard die, the outcomes, what you'll get. So if you look, I've listed here, so if I roll 2 standard dice, there are the outcomes here for the first dice and the second dice. And we're looking at the sum of those. So if I can roll 2 1s, which gives me 2, a 2 and a 1, which will give me a 3. If you count up the total outcomes that we have listed here, there are 36 total outcomes. So when I'm finding my probability, that's going to be my bottom number, my total number of outcomes. Now we want to find the probability of rolling an odd number, and this really means the sum of an odd number. So if I look through here, my odd numbers, let's see, we have a 3, we have a 5, and we have a 7. And then here I have a 3, a 5, a 7. And you'll notice that it's going to start to form a pattern. Then we have a 5, a 7, a 9. There's 3 from each column. My odd numbers, the sum of the odd numbers, every other one is going to be odd. So out of the 36, we will have 18 odd numbers out of 36, or if we simplify it, it becomes 1/2. Let me erase this part so we can look at it again. Okay, next we have the sum of a 7. So I got to go look at my chart. Down here, 6 plus 1 is 7. And then 5 plus 2 will give me another 7. 4 and 3, 3 and 4, 2 and 5, and 1 and 6. So those are the only ones that will give me a 7. And out of my 36, it was 6 out of 36. And that, if I simplify it, will give me 1/6. Next, we want the probability of getting a number 3, a sum of 3. So let's see here. We can do 2 and 1 and 2 and 1. And there's really no other way to get a sum of 3. And if you look at the outcomes, it's not there. So we're going to have 2 out of 36. Or if I simplify it, 1 over 18. Let's see here. Our last one is, let me erase. All right. The number 14. If we look at our chart, here's my highest total. 6 plus 6 is 12. It is impossible to roll a 14 because I only have 2 standard die that go up to 6 each. So that probability, it's sure thing that it will never happen. It's 0 out of 36, or it equals 0. All right, here we are looking at probability in a deck of 52 cards. We want to find the probability that you draw the following from a standard deck of cards. We have a queen, a diamond, a card greater than 3 and less than 7, the Queen of Spades, and a picture card. Now, here are your outcomes for your standard deck of cards. You have 4 suits with cards, and each suit has 13 cards in it. So you have a total of 52 cards. The first suit is your diamonds, and they go from ace through king. Then you have clubs, and they also have ace through king, hearts, and then spades. You also have 2 of each set. You have 2 red sets and 2 black sets. And those are things that we'll need to look at. So for our first one, to find the probability of drawing a queen, we have 1 queen in each suit. So there's 4 total queens. So it'll be 4 out of 52. Or if we simplify it, it's going to become 1/13. And let me erase this part. Okay, next, a diamond. All right, diamonds, there are 13 total diamonds. So that's going to give us 13 out of 52, or 1/4. Next, we are looking for a card greater than 3 and less than 7. So we don't want to include 3 and 7, but we're going to include 4, 5, and 6. And they didn't give us any color specification. So it's going to be 4, 5, and 6 from all 4 suits, which will give me 12 out of 52, which I know we can divide by 4, and it will give me 3/13 when I simplify it. Next, we have the Queen of Spades. So here are my spades right here, and there's only 1 queen, so that would be 1 out of 52. Easy, it's already simplified. And then our last one is a picture card. Your picture cards are going to be just the queen, king, and jack. We don't include the ace for our picture cards, so it is just the ones with like the faces on them. So there's 3 in each suit, and there's 4 suits. So that's going to give us 12 out of 52, which again we can divide by 4, so it gives me 3/13 when I simplify it. So in the past, in the last 2 slides, we were looking at theoretical probability. It's what should happen based on the outcomes that are given. But when we do theoretical probability, so we know what should happen, but then you should know, like when you flip a coin, you don't always get heads and tails 50% of the time. So we have empirical probability, which is what does happen. So they know the theoretical probability, and then they conduct an experiment and they get empirical, which is what does happen. And the law of large numbers says the more that you repeat an experiment, the empirical probability gets closer to the theoretical probability. So if I do an experiment 10 times, my probability, if I was flipping a coin 10 times, may not be close to 50% for heads and tails. But if I flip it 1,000 times, it will probably be a lot closer to that 50%. It may not be exactly 50%, but it'll be closer. So here we have a chart that lists the marital status of the U.S. population, ages 18 or older, in millions. And we're going to use this chart to find out the probability if one person is selected randomly from the population, find the probability, and they want it expressed as a decimal rounded to the nearest hundredth, that the person has never been married. All right, so let's see here. Never married. We have male and female, but we want just the person. So we need the total. We need the 69.2 over the total number of people, which is 235.8. And this is in millions. So it's 69.2 million, 235.8 million. When I find it and I divide those two and I round it to the nearest hundredth, I get 29 hundredths. So you want to look at your chart and see what totals you need to get the total amount. All right, our last slide for 11.4 and for this video will be you select a family with 3 children. M represents a male child. F represents a female child. The set of equally likely outcomes for the children's genders is you can have 3 males, or you can have 2 males and a female, or, and this includes birth order, so we could have then a male, a female, and a male. And you can see all the rest listed here. They want us to find the probability of having exactly 1 female child. Well, if we look at our outcomes, there's 8 total outcomes there. And out of the outcomes, having exactly 1 female child, there's 1 here, 1 here, here, and that's it. So it would be 3 out of 8, which is in lowest terms, so we don't have to simplify it. All right, next, exactly 2 male children. So that would be, let's see here. All right, we have 1 here, 1 here, and 1 here. And that's going to be it, because if you have 1 female, you're going to have exactly 2 male. So it would be 3 out of 8 as well. Then at least 1 male. So they have to have at least 1 male. They could have more than that. Here, the probability is going to be 7 out of 8 because they all have males except for the one where it's all females. And then fewer than 4 female children. Well, they're only having 3 kids. So all of these have fewer than 4 female children. Some have 0, some have 1, some have 2, some have 3. So that is a certain thing. It's going to be 8 out of 8. Or because it's certain, it will equal a 1. Or 100%.